We're going to go ahead and get started. Is the definition, but it should seem familiar, and as you write it, as we talk about it, when you realize the familiar aspect, I want someone to jump in and tell me why this is familiar, in spite of the fact that it's technically new. And it is separable differential equations. Now, we can kind of preview what the term means by looking at the individual words. Well, obviously, let's start with the most familiar, and I don't mean equations. I don't think we need to discuss that one. Differential has a derivative, right? And it is definitely involving a derivative, right? So our equation is going to have a derivative in it, all right? What does separable mean? You can separate it, right? So an equation of the form, and I'll go into that. So this looks a little scarier, and this doesn't look familiar, but I'm going to show you what it is, how it's, or why it's familiar if you don't see it after I write the next part. All right, so an equation of the form, and it is Monday morning, so I don't want to get my brain off track here. dy dx equals f of x. No, I'm sorry, I lied. F of y is what they're doing. Of course they would do that to me. F of y, g of x. That's terrible handwriting, I'm sorry. I haven't used this enough lately. It's Morgan's fault. I think she just apologized to the screen when she watched it. Which one a bit? F of y. Remember how you came back and watched the video, fourth block, when you had junior leadership, and it was just me and you in the room, and you paused the video to tell me that it felt like I was talking just to you? That's what I was getting at. Thanks, Marquise. All right, so not very familiar looking yet, and this is called separable, and I'm not going to go into all the details of it. I'm going to leave it at that. We separate the variables by writing it in the form, and I'm not sure how I feel about this, but we're going to go with it. 1 over f of y dy equals g of x dx. Now this is the point at which you should be able to tell me why this is familiar.
Isn't that kind of like different? Yeah.
Well, it's kind of the same thing whenever you would have a dy over dx and you like put the dx on this side because they had the x.
That's exactly right. That's how I got you ready for this. Just having you go ahead and realize that when you're going to solve a differential equation, that you should get in the habit of separating first. Because if what I've run into in the past years is that if I don't do it then and I wait and do it now, it's not habit enough. You know what I mean? Because it's too late in the game. Sort of, you've already developed the habit of seeing it another way. But if you have a free response question where you are solving a differential equation and you don't separate first, most of the time that section will be worth 5 points, of which you will get 0 points if you don't separate first. Even if you somehow wind up with the correct result, you get 0 points for whatever you put between where you failed to separate and where you got the correct equation if you don't separate first. So let me emphasize the importance of it that way. And then how would we solve this? You're right, we take the integral of both sides, right? Now, and I'm going to read you this sentence, and I don't think we need to write this just because I've already kind of got you in this mindset. And that was why I asked you in the form of a question as opposed to telling you this definition, because I wanted to make sure that had sort of planted itself in your brain already. But the final sentence in the definition box is, the solution is found by anti-differentiating each side with respect to its thusly isolated variable. Oh!
2 strikes.
It's this dang computer. I don't know why it's suddenly doing this again. I need a volunteer. Who wants to sit over here and babysit my computer? Will you, Marquise?
Yes.
All right. Don't do anything stupid. I'll send you back to West Point.
So, wait, what do I have to
Just yeah, touch the mouse every little bit.
Is 20 that sentence really ironic?
Don't do anything stupid or I'll send you back to West.
And I promise you, when you go back there, it's not going to be Disneyland anymore. That's how it works. Anytime college is recruiting you, whatever they're recruiting you for, that's how it is. You're like, I can't wait to get there. And you'll be calling home about the third day. Can I come home, please? All right. The law of exponential change is the next thing we need to talk about. Okay. Parts of this are going to be very familiar, but this first part becomes very important in the context of what we're doing here, because of how you will see questions pertaining to this section worded on the AP exam, and you will see questions pertaining to this section on the AP exam. And I say questions plural, because that has been my experience with exams, that everyone I've seen has multiple questions pertaining to this one little lesson. It's not hard, it's just important that you get the terminology and have the right keywords in your brain. All right, so, and this is a very important phrase, and your book doesn't do anything to emphasize it, but if y changes at a rate proportional and this is what I want y'all to do. I want you to underline changes at a rate proportional. Because you will see that phrasing, and that's supposed to let your brain know that the equation they're talking about is what we're going to write in just a minute, okay? To the amount present, and I'm going to pause right there and talk about that wording, because the wording is formal, as most definitions are, but what does that mean? Okay, if something is changing at a rate proportional to the amount present. Can you think of an example? And I don't mean a specific example. Can you explain what that means?
So like if you got like one block, well 2 blocks, then you like get 2 more.
Oh, no, that
It's
means
like interest.
that means it's like exponential, because the less that you would have, the lower the rate increasing would be, and the higher that you have, the faster it would go up.
Very good, Becca. Everybody needs to eat an orange before calculus every day from now on. Yes, that would be a situation where whatever you have determines how fast something grows, because if it's a rate proportional to that, I mean, the only thing I would argue there is that if for some reason you, well, no, I'm not even going to argue with that. I don't want to make it any more confusing. Do you understand what you're saying?
Yeah.
So, like, if I have a lot and it's proportional based on that, then that's going to affect my growth rate, right? Okay. So, and then parenthetically, they say that is, and I used to not have students write this, and then I realized it wasn't as simple as I was making it, apparently. So we'll see if we can't make it simple for you this time, doing it this way. That is, if dy dt equals ky, and I want you to, again, underline that equation. And the point of this underlining is to let you know that when you see the phrasing at a rate proportional, changing at a rate proportional, that's this equation. So that's the reflex that should happen in your brain. When I read that phrase, I write this differential equation. You with me? Okay. And if y equals y sub 0, and what does that mean? That's right, that's the initial amount. There was a time when y'all wouldn't have known that without me reminding you, but I had to make sure. When t equals 0, which if you know that y equals y sub 0, then that's sort of redundant to say when t equals 0. Then y equals y sub 0 e to the kt. I'm going to stick with their letters. That should look very, very, very familiar, does it? You have a nickname for this guy. It's what? Pert. That's Pert. Your old friend Pert with new letters. Where's the P? Y sub 0. And what's the, obviously the E is still E. What's the R? K. And T is still T. Right? So this is just Pert. All right? And we want to go ahead and define these little parts. K is the growth constant, and we'll do this as a bulleted thing at the bottom instead of sentences. K is the growth constant. If K is greater than 0. Now, let's pause there and see how much pre-cal we remember. What would happen if, okay, first of all, does everybody have sort of an image in your head of what PERT would look like on a graph? Definitely exponential.
Go up.
Okay, why is it going to go up? If K is positive, and presuming that your Y sub 0 is positive, right? Okay, where does this exponential graph cross the y-axis? Oh my goodness. I've been teaching my little 1B kids this for the last...
That your initial?
Oh, yeah, exponential, y sub 0.
That's right, at Y sub 0. Remember? The exponential equation when you... And this becomes important if I'm working without a calculator and I want to think graphically about the situation they're describing for me. Really important for me to know that my y-intercept is the coefficient in exponential growth, right? Mm-hmm. And then now let's get back to the requirement that K is positive. If I changed K to a negative number, then what would that do to my thinking?
It would make it like that would make the E a really small number to be a real name.
Yeah, flip it over.
So what would that do to the graph?
Flip it over.
That's right. It would reflect it over the y-axis. It suddenly becomes decay, right? If K is positive, we have growth. If K is negative, we have decay. Because like Becca said, that reverses everything. So all my whole numbers are going to give me fractional exponents now, right? Or not fractional exponents, but it's going to put the E in the denominator. And all of my fractions, because they get changed to negative, right? It does it the other way around. Does that make sense? Okay. All right. I probably didn't even say that right, but I'm doing my best. Okay. So that would be the growth constant if K equals 0. So what do you think we would call it if K is less than 0? There you go. So Mackie, when you're tutoring your kid again, you can let him know that.
We already did this.
Dang it. Yes, you will use that. Yeah, but when you're reviewing him for his exam, you can tell him, yeah, you actually do have to know. You don't do exams?
I don't remember doing it in the 8th grade.
It's called an EOC. Maybe it was just too easy for you. Yeah. Then they go into an example here, and whether or not we need to write this, we probably do. All right. Let's go ahead and put this heading in here. Continuously compound or compounded interest. What's compounded interest?
Builds on that just
Over
less.
time. Interest over time.
What did you say, Austin?
It like builds on what it just was previously.
What do you go a step further with that, because I think you're saying the right thing. I just want you to say it better.
Okay. Like an example, like if you had $10 and you gained $5, and next week you gained another $5, it wouldn't add to the 10, it'd add to 15.
Not quite.
But like if you're getting 10% of
Okay, well, let's back up a step. What is interest?
interest is money.
All right, so let's say your parents start you off when you're 5 years old, and they give you an allowance, and you have to put your first $5 in a savings account. And they're not gonna let you touch it until you're like 100 years old, all right? Let's just say you were born at a time when the interest rates were crazy high, and we're gonna use Jack's example. Your interest rate was 10%. What does that mean?
You get 10% of
Increases
that
by 10%.
$5.
That's right. You're gonna get paid 10% over some time period for however long you leave the money there, right? Okay. Well, if they kept paying you 10% of $5, you'd be getting the same amount of interest every time. So you're only getting paid interest on the $5, and that's pretty much how savings accounts work, by the way. If you borrow money, your interest is compounded continuously. All right, so what that means is compounded interest is interest paid on interest. So if I borrow money and I'm paying 3%, if I get a really good rate on something, and I'm paying 3%, then the interest I pay is not only on what I borrowed, it's on whatever the balance is at the time that I pay it. Does that make sense? So I'm paying interest on the principal, which is what I borrowed, and I'm paying interest on the interest. When you go to college, and I think they've changed some laws since my kids were in college, but they love to have little booths set up to try to get you to sign up for a credit card. And they make it sound wonderful. But there's been lots of kids parents have taken them to court because of the fact that they did a little shell game with you and didn't tell you about all that interest and how all that works, and they know you're a sucker because you don't know better, and you sign up for the card and you go spend a bunch of money, and then it's bad. You never get out of it.
I was like, no. I love my credit score.
There you go. That's what you need to do. You need to not have any credit unless you have to have it, and then you need to guard it like your life, because in essence it becomes your life in this culture. So that's what compounded interest is, and that's important just to help you understand where we're going with this and where you're going in your future. All right, so you should recognize this next formula, and I'm going to also, and I debated Friday about doing this in advance, and I was like, no, maybe we don't need this year. All right, we had PERT, our good friend we just talked about, and then we have this formula, and again, this same formula appears in all sorts of math books with various letters used, but I want to stick to good old calculus book letters because this is what you're going to see. So we have a sub 0 times the quantity 1 plus r over k raised to the kt power. Y'all remember that guy? Okay, what's the difference between PERT and this guy?
You have the one, like that's inside. You don't have an E. You have
Okay, yeah, in place of e, basically it's the same formula with some different letters representing y and y sub 0, right? But still the same, they still represent the same quantities. But our base is now 1 plus r over k. When do I use PERT and when do I use this?
If it's compound interest, you use this, and if it's normal interest, you use the other.
when it's the same rate, like the same rate, you use the other.
When your rate is changing, or
Rate is proportional, use the other one.
Oh, stop.
When it's constant, you use the first one.
What do you mean when it's constant? Because again, you're on the edge of the right idea, but I'm not sure you're saying the right thing.
Like a savings account, like it's 10% each time over the course of the years.
It's 10%. What do you mean each time?
Like it's always based on the principal, right? Instead of the interest plus principal.
Well, no. It's not a, okay, you use PERT, and I think y'all are getting at the right thing, but let's move us on. When you use PERT when the situation involves continuous compounding. Okay? That's when you're going to use PERT. Does that make sense? And now, based on this definition we just had of the law of exponential change, and I had you underline the phrase changes at a rate proportional, and I have the differential equation dy dt equals kt, right? So in other words, some rate times time as my derivative, then that's PERT. And we can antiderive that, and I'll show you that in just a minute. But so you use, if you think back to algebra 1/2 / pre-cal, you use PERT anytime the rate is compounded continuously. The word continuously tells you that we're talking about PERT. I can tell by the lack of conversation and what conversation is being had about this that I am going to give you the handouts I gave you last year again before you leave today, hopefully. But this formula that we've just written is for discrete compoundings. Now, what does discrete mean?
Oh, do you know what that means?
No, that would be EET. Discrete compoundings. What was that?
Oh no, I thought you said the street kind of down, like you gonna be out on the street.
Discrete means countable. A number is given, okay, as opposed to continuous. If something is happening continuously, can I count it?
No.
Okay? For the same reason I can't count the numbers between 1 and 0, right? Because there's an infinite number of numbers there. Same kind of idea. You can't count that which is not countable. And these are the countable versions, okay? So in this context, your differential equation, and I will abbreviate that to DIFF-EQ, which if you ever take a course in this stuff, you will call it DiffEQ, and you see why. Marquise, you are falling down on the job, dude. I need you to do better. I'm serious. All of us. I'm calling West Point. Tell them to cancel your offer. All right. He's like, God, why'd I ever tell her I was going to West Point? DADT equals RA. Now compare that equation to the one we had in the, which one was that? That was the law of exponential change, yes? Do you recognize a parallel here? What is this parallel to?
The R's the K.
It's back to that R is just K, right? So I don't want you to think you have a whole new set of stuff to learn here. It's the same thing you've been doing the whole time. It's just a matter of what you remember about it. And of course, your initial condition is that A of 0 equals A sub 0. Does that make sense?
So that right there is basically the same as D1 dt equals KT. That's what you just said.
Yeah, the DADT, yes.
Did we put KT or KY?
It was KY in the other one. Yeah, because now we were expressing it in terms of, we were expressing our derivative, and you're right, I messed that up. Oh, no. A is Y, right? Let's get the correlation in our minds. Because if you don't get this, the next question I'm going to ask you is really difficult. If you get this, it's really easy. You with me? All right, so A is Y. I thought I had written X, T there instead of A. That's why I was double checking. All right, A is Y, not if you agree. Okay, T is X, right? And K is R. We'll look back at the one we had from the law of exponential change, and it said, and I'm going to read exactly what it says so that I don't misspeak or tangle something up. If dy dt equals ky, then y equals y sub 0 e to the kt. Got it? And that's written on your paper, right? Okay. So now, tell me what to write in terms of the notation we just described here. I'll start you off. A of t equals. So in our law of exponential change, we had a y that was expressed in terms of x, yes? Now we have an a that's expressed in terms of t, right? So compare this to what we got as our y equation in the law of exponential change and tell me what this one's going to be.
T sub 0.
A sub 0 e RT. That's it. Does that make sense? So if the rate is proportional to the starting amount, you're dealing with PERT regardless. Okay? And that is your solution. This is probably a good time for me to show you that solution. So let's do that next. All right, here's what we're going to do. And I'll be honest with you, I have students over the years, I've had varying degrees of success with this. So if what we're about to do blows your mind, and I know it is Monday morning, then just bear with me because you'll be okay not to completely understand this. If you just remember that when you see the rate change is proportional, or if I have dy dx equals 7x, then I just know what my y equation is just from that derivative. All right? So let's do the generic form that they gave us in the law of exponential change, which was dy dt equals ky. And by now you probably understand why I'm being so careful about the letters here, because it's all saying the same thing in just in different letters. Just like these formulas are when you see them in different books. All right, now this is where I would ask you not to look at your books, because this is actually in the book for you. All right, let's pretend that we didn't know all these new rules, and I told you to solve this, and maybe I should have given you this as a warm-up. And in fact, just to make life a smidge easier, let's change our k there to an actual number. We'll change it to my favorite number, 8. So let's just say that I flip over to number whatever, and I see that dy dt equals 8y. All right? And my job is to figure out what y is. So let's do it like you've not had any of the conversation we've had this morning. Let's do this problem like we would have done it last week based on what we knew last week. All right? Well, what did I tell you when you're solving a differential equation is the first thing you should do? Well, y'all are saying the same thing two different ways, right? So we're going to get the dt on the right. And what about that y? It needs to divide off. So I'm going to have dy over y equals 8 dt. Yes? Okay? Now I'm going to switch colors because we're going to go into official solving mode. How do I make a dy and a dt go away? Antiderive or integrate. So I'm going to integrate both sides. And you might need your integral reference sheet in front of you if you don't know this. What is the integral of 1 over y? ln of y equals, what is the integral of 8 with respect to t? 8t, right? Plus c. Thank you. And it might bother you, and we haven't really talked about this yet, but when you integrate, how do I know when to use the c and when not to use the c? Let me pose it as a question. That's right, if it's indefinite. How do I know it's an indefinite problem? I don't see limits of integration. I don't have an a and a b given, right? Okay? Well, we just integrated both sides. Well, you only need to put the c on one side. Why would that make sense?
Because you can add a constant to either side.
That's right. Well, okay, I was going to say, what if I added a constant to both sides? What would I have to do? What would my first step for isolating y be? I would subtract that constant, right? Well, if I have some unknown constant on the left and some unknown constant on the right, and I subtract, what's going to happen? I'm going to get a new third unknown constant, right? So the universal practice is just put it on the right. It saves you that step because you're going to solve for y anyway. Does that make sense? Okay. So now, if I want y by itself, what do I need to do? I need to raise both sides as exponents of e, right? Now, your book probably doesn't show that step. They do not. All right? The other thing you need to get in the habit of, and I intentionally left it off because I want you to just get comfortable with this idea. When you take the natural log of something, why is the domain an important restriction to consider? That's right, because you cannot take the natural log of a negative or what, Austin?
Zero.
Or 0. And why does that make sense graphically speaking? What does that graph look like? That's right, it comes up hugging the y-axis on the right side and then grows. But both the logarithmic graph and the exponential graph are, when we're talking about growth, they're both positive derivatives, right? So they go up forever. Does that make sense? Okay. So if I take the natural log of a variable, what immediate requirement is placed on that variable that was not there until I did that? It has to be greater than 0. Well, I can make that happen by putting absolute value bars. So every time you take the natural log of a variable, you need to include that, okay? For that reason. Does that make sense? Okay, well, then the natural log goes away and leaves me the absolute value of y equals. Now, this is where it gets interesting. This is like, how well do you know your exponent properties? And if you don't know them, you're going to get better from here to the AP exam. All right? If I have E raised to a sum or difference of terms, there is an exponent property that you got really good at using going in that direction. Now we're going to use it going in the opposite direction. Because I can break this apart into e to the 8t times e to the c. Why can I do that? Because if I am multiplying a pair of powers, and I erased it, I was hoping I still had it on the board where I did this with my 1B class last week, as a refresher, because we're about to take a test on the exponent properties. If I have a power times a power, that is like x squared times x cubed, what would that give me? X to the fifth. Well, if you look at what we just did here, if I wanted to put that back together as 1e, how could I write it? E to the 8t plus c. Does that make sense? All right. Now, what about this e to the c? What's c? Some number we don't know, and now I have e to some number I don't know, right? Well, that I'm just going to call that c sub 1. So now I have c sub 1, e to the 8t equals the absolute value of y. And I intentionally saved this last step as a separate step because I know it's going to blow your minds a little bit.
Why do we move the C to the front?
Because that's the traditional way to write anything that's got an exponent in it. You save it as the last term.
Oh, so you just,
And well, let me ask you this: if I had to multiply e to the 7x times 10,
You put the 10 in the
the
front.
10's going to that's just a coefficient, right? So I'm just going to pull it out to the front just because and that should be reinforced by everything we've done with derivatives and antiderivatives, right? Because you always pull the constant out. Does that make sense? So it's just a constant number, right? So does that make sense? Y'all with me? Do you recognize that right side? What is that right side? Pert. Okay. All right. Well, if I have the absolute value on something, this is something that should have been taught to you in your Algebra 1 class and then reiterated in your maybe geometry, but definitely Algebra 2 class, and apparently it wasn't because I remember having to go over this during pre-cal. There are two possibilities if I want to drop the absolute value, and that makes it plus or minus c sub 1 e to the 8t, right? And then, to close out our little proof of what we've been talking about as far as the law of exponential change, so all we have to do is let c sub 1, I'm sorry, plus or minus c sub 1 equal a sub 0, and then our y, or not, I'm sorry, I'm switching variables on you. That was bad manners, bear with me for a sec. Plus or minus c sub 1 is equal to y sub 0, since we're in y's. So y equals y sub 0 e to the 8t. Now, I have had students from both extremes on this little concept that we just did by doing this example. Some do this on every problem, I guess just to show they can. You may encounter a free response part of an AP question that requires you to do this. Okay? So it wouldn't hurt you to do this on a few problems on the test, on your homework today. On your homework for this lesson, just because you may encounter that on the AP exam. But do you see how this makes perfect sense? Somebody connect this back to the law of exponential change for me. It's written in your notes. It's not something you should already know. Basically, this is the same thing, right? So what did we say? We said, what does the law of exponential change say? It says, if I am given dy dt equals ky, right? And I just changed the k to an 8 so we'd have one less letter to think about. Fair enough? So if that worked with 8, doesn't it stand to reason that it doesn't matter what 8 is? As long as it's a number. Okay? So if I'm given dy dt equals ky, then we're talking about exponential growth, and the corresponding equation for that growth is y equals y sub 0 e to the kt. Does that make sense? And now it should make sense to you here. And if it doesn't, we need to work on that. That is, you probably need to work on it by actually doing a few. All right. Radioactive decay. What is radioactive decay? You're like, oh, we were actually supposed to remember that?
Is that like Half-Life?
It is. It's very much related to Half-Life. Science and math start to merge in many ways for you from here forward. All right. And I like the explanation of radioactivity in this book, probably as good as, in fact, maybe better than any math textbook I've seen it in. I'm just going to read it to you because I think it's worth thinking about, because you need to defuzzify the concept of half-life because it's not difficult, okay? But you don't need to oversimplify it to the point, oh, I'm just going to put a half. Well, think about what it means. When an atom emits some of its mass as radiation, think about the phrase right there. It emits some of its mass. I wish humans could do that. Obesity would be a thing of the past. You know what I'm saying? Like, I could just decide today I'm going to emit some of my mass. There was some little mechanism I could trigger, some food I could eat, some pill I could take that would make it just go away into the wind. All right, when an atom emits some of its mass as radiation, the remainder of the atom reforms to make an atom of some new element. This process of radiation and change is radioactive decay accounting for the fact that it's losing part of itself, right? And an element whose atoms go spontaneously through this process is radioactive, okay? So the next time you hear reporters screaming about radioactive isotopes, you know what they're talking about now. Radioactive carbon-14 decays into nitrogen. Radium, through a number of intervening radioactive steps, decays into lead. Did you know that? Pretty interesting, huh? Experiments have shown that at any given time, the rate at which a radioactive element decays, as measured by the number of nuclei that change per unit of time, is approximately proportional to the number of radioactive nuclei present. Do you hear that? Did you hear a phrase there that I told you? Rate proportional. We have a proportional rate, right? So that means the derivative equation would be dy dt equals kt, or, you know, whichever variable we're using, all right, is approximately proportional to the number of radioactive nuclei present. Goes back to what Becca said to start with. How much you have depends on what you just had, right, at any given time. All right, thus the decay of a radioactive element is described by the equation dy dt equals negative ky. And then notice right behind it they say k is greater than 0. And they're using an emphatic negative sign to remind you that your derivative would have to be negative to make this happen, right? Doesn't that make sense? Based on the graphical conversation we were talking about a while ago, or interpretation. If y sub 0 is the number of radioactive nuclei present at the time 0, the number still present at any later time t will be y equals y sub 0 e to the negative kt. The half-life of a, and maybe for the radioactive decay, I just want you to have an understanding, and I'm going to put C page 356. Now, to truly understand this definition is not a requirement of the AP exam, but it will come up enough in your math and science classes that I think, to me, just rereading that in the context of the conversation we had this morning should help clarify a lot of things. But probably the most important component of radioactive decay is half-life. And it is half-life. One phrase, one term. And do you know what it is without reading it in the book?
That's like whenever, like if you started with, your mass was 1/2, then it would go to 1/4, and then it would go into.
But what specifically is the half-life in what you just said?
It's half of its original, a half of the previous mass.
You're right. It is a half of the previous mass in whatever time unit we're talking about. But what is the half-life?
How fast it decays? The rate.
It's the length of time it takes for half of it to go away. Okay? So write that down. It's the length of time it takes for half the substance and I'm going to use their phrasing from that paragraph just to emphasize why I want you to understand it. Emits as radiation. And then I want to add to that. Now, the definition in your calculus book doesn't explain any of this, but I think, to me, it helps me understand what I'm doing if I know what it actually represents. Here's the definition in your book. The half-life of a radioactive substance with rate constant K greater than 0, is the natural log of 2 over K. That works everywhere. Okay, and what does K represent? K is the rate constant.
This is what we use like find that wrong.
Yes. Yes. Yeah, you can use this in your science classes too. And again, I could prove that to you with another little equation we solved like we did a while ago, but just trust this for now. And if you want to prove it to yourself, use the same tactic we did for solving that differential equation. All right, so notice when it says the rate constant, that means something's happening at a constant rate. Okay, don't think that because the words are rearranged, it means something new. Okay, so that is pretty much everything in this lesson. I'll be honest with you, I have never taught Newton's law of cooling or something like that. Let's jump over. Now, this is another one of those lessons. If you just sat through this theoretical conversation where I was trying to pull from things you already knew and you were like stumped on many of the questions I asked, don't panic, because the examples are about to show you that there truly is, as I promised Becca, I don't know how many of you heard her ask in my answering, how hard this lesson is. This is not a difficult lesson. Okay, this is a nice little break after U sub and parts.
So does this will we have to use these southern parts in this lesson?
Probably, possibly. More likely, the first few you won't, and then they'll throw one in just to see if you're paying attention. Yes, because from now that you've learned those techniques, and that's an excellent question, Becca, but now that you've learned those techniques, it's important that you remember you have a protocol in your brain. What is your first and best hope when you have to take the integral of something? That we have a rule for that, right? Okay, well, what if we have a rule for what I'm seeing, but what I'm seeing has, instead of an x, has like an x squared? That's a U sub, right? So if it looks like a chain rule problem from derivative land, it is a U sub problem in integral land. Does that make sense? All right, well, let's just say it's something crazy like e to the 3t times the cosine of t. How do I know that's parts? There is no relationship between the two functions. They're from completely different camps. One is not the derivative of the other, right? That's sort of you need to be going through the program as you do these. So, very good question. All right, we have dy dx, and we're doing number 2 here on page 361 if you have your book open. If you don't worry about it. Equals negative x over y, and then it says y equals 3 when x equals 4. And I will read the directions while you write the problem. Use separation of variables to solve the initial value problem. Indicate the domain over which the solution is valid. Let me also warn you that the authors here, as any textbook teaching you this concept as a new idea, would state it in the directions. On the AP exam, it's not going to say use separation of variables to solve. It's going to say solve. It's going to ask you what y is. It may not even use the word solve. So you might be given something like this, and then you're asked to write an equation for y. Okay, well, here's how you should think, and this is the process your brain should go through. You're like, oh my God, I have to write an equation. What? Well, what do I have here? dy over dx. There's my y, right? And y is wrapped up with a d. Yes? Okay, so if I want to solve this equation for y, what is the first order of business? Sort your x's and y's. So segregate the x's and y's. Put the y's on the left. That's just what you're more used to. There's nothing wrong with doing it the other way around. You just look a little unique. If that's what you're after, go for it. All right, so I would, in this case, multiply both sides by y. So on the left, I'm going to have y dy. And on the right, I'm going to have negative x dx. Now, a general rule of thumb for you is that you should never put anything on the left that you don't have to. You want to put why would it make sense to put the least amount possible on the left?
Because you're just gonna take it off.
That's right. I'm going to have to take it back off if I put it over there and it didn't need to. So things like constants, like this negative sign, should stay with the x stuff. Because my ultimate objective here is to get y by itself, right? Okay. Here we go. You tell me. I'm going to switch colors again. We're going to take the integral of both sides. What is the integral of y? Y squared over 2 equals, and why didn't I put a c there? Because we're only going to use one and we're going to put it on the right. For the same reason we don't want to put one on the left and then move it to the right, we're not going to put one on both sides either, right? So then this gives me what on the left? I'm sorry, on the right? Negative x squared over 2 plus c. Now, this is where I take my own little path to the answer. Every textbook I've seen suggests that you go ahead and solve for y. I don't see why you would do that. Because if I have an initial value given, I would stop right here and then come back and solve for y, okay? So now I'm going to take a little side step, and I'm going to replace x with what it is and y with what it is. What's my y? 3. So I'm going to have 3 squared over 2 equals negative 4 squared over 2 plus c. Because now just this step is just to figure out what c is, right? Well, obviously 3 squared is 9, so that's 9 halves equals negative 16 over 2, which would be negative 8, yes? Plus c. And then I want to add the 8 to the 9 halves. How many halves are in 8? 16. So if I add 16 halves to 9 halves, I have 25 halves is my c. All right, so now I'm going to come back on the next step after my y squared over 2 equals negative x squared over 2 plus c. I now know what c is, don't I? And what is it? 25 halves, right? Well, if ever there was an equation screaming to be multiplied by 2, I believe this would be it. So the next step would be y squared equals negative x squared plus 25. Yes? All right, and then I'm going to take the square root, and I get, and here on the inside I'm going to go ahead and write 25 minus x squared. Because if you know you can't take the square root of a negative, it will bother you if what's inside your square root equals, has a negative as the first thing you see inside it. It's just a little bit distracting, but 25 minus x squared makes it okay. All right? Y'all with me? All right, and then plus or minus in front of it. And the rest of the directions said, indicate the domain over which this solution is valid. Now, if you'd been listening to good old Twitty since last year, something should have jumped in your brain when we wrote y squared equals negative x squared plus 25.
It's a circle.
It's a circle. If x and y are both squared, because if I added x squared to both sides, I'd have x squared plus y squared equals 25. It is a circle, and what kind of circle? Centered at the origin with radius of 5, right? So you got that pictured in your head? All right. Well, if we eliminate this down to a function, because that would be a circle, and we don't want that, what would we need to do to change our final result there?
Make it either the top half.
Right, either the top half or the bottom half, and we typically stick with the top half, so let's take that plus or minus off. So does everybody see the top half of the circle there? All right, so what's my domain? From negative 5 to 5.
Will you always have like a plus or minus in front of these, or?
That's a good question. Brackets. I agree with you that it should be. The one I had in the book was parentheses. I don't know why, but let's go with brackets. I like brackets better. Why do brackets make more sense? Oh, wait. Let's think about it. Let's think about which one we need there before I say anything else. Any thoughts?
You'd have parentheses, because if you were, because 5 squared would be 25, and you have a 0 in your radical. So
Is a 0 under the radical a bad thing?
No.
Okay. So if I have negative x over y, and this is the top half of a circle,
Y can't equal 0.
can y not equal 0?
When it's in your, and when your derivative, it would be, give you Y's on the bottom, so that would make it undefined.
Does that make sense? The domain of your derivative equation, why can't y be 0?
It'll be good and fine.
Yes. I love it when y'all can come to stuff without me telling you. That's perfect. So let me undo. I think.
Miss Twenty,
There it goes. Yes.
are you always gonna have like a plus or minus out front? Or-
Well, typically you want to, but whether or not you include it depends on whether or not it gives you a function or not.
Okay.
And that won't be as big of a question as it feels like it would be right now.
Okay.
So that's your equation for that one. Pretty simple? All right, let's do let's do number 10. And we have dy dx, for those of you whose book is not open, 4 on the square root of y, ln of x, over x. Are you excited yet? You should be like, yes, let me at it. Y equals 1 when x equals e. Come on, guys, breathe and be happy. Like, do I have to be happy? Okay, well, just, all right, here, and this is another thing. And one of the reasons I like to throw these at you at random points in our conversations these days is that progressively I'm trying to build up in you the, I can handle that. That reflex needs to get in there, okay? Now, the way that happens is that you look at this and go, okay, wait a minute. If I'm solving, and literally you should either close your eyes, turn your paper over, or whatever you have to not look at this hideous equation, because you probably find it hideous, yes? I find it awesome. Okay? Just in case that shocks you. Yes? What should we do? How do we solve the dy dx equation? Yeah, and so we're going to separate and integrate. That needs to become your instinct. All I got to do is separate and integrate, right? So if I separate it, maybe it won't be quite so hideous, right? So what do I want on the left? Anything that has a y. So the dy is going to stay there, right? And what else do I have that has a dy? Has a y in it? The square root of y, and it's in the numerator of the right, so how would I get rid of it? So put it in the denominator of the left. Does that make sense? Okay, so that's the only y stuff I have, which means everybody else is going to be on the right. Make sense? Maybe I shouldn't, but I'm going to do you one more favor. When I write what's left, I'm going to write 4 times the natural log of x times 1 over x dx. Do you see what I'm saying? By spreading that out and looking at it, suddenly it's not so bad, is it? Okay? It's still bad? That's because you spent 2 days at West Point instead of here doing parts with us. Just saying. The Reaper is here. Okay, so on the left, I don't want to think of that as dy. Well, first of all, we're going to integrate, yes? But I don't want to think of that as, go away. Dang it. Let me pull my board down where I can write on it. The little thing kept jumping in the way. All right. I don't want to think of that as 1 over the square root of y, do I? How could I think of that as y to the what? To the negative 1/2, right? So make yourself a little note out to the side. And I made that, the way I wrote that kind of looks like it's multiplying, but that should be over in the margin of your paper, a little tiny y to the 1/2, or at least negative 1/2. At least be thinking that, right? Because then its antiderivative is what? 2 to the 1/2 equals, yes? Right? Everybody with me? Okay, I thought I heard some dissension there. All right, then on the right, what's the first thing I'm going to do?
Yeah, pull up.
I'm going to pull that 4 out, right? And I'm going to come over here, and I have a natural log of x and a 1 over x. Why does that little pair of functions make me happy? Because there is a derivative relationship, right? Okay, so which one is what? Well, first of all, what method am I going to be using here? U sub. It's just U sub, right? Because they're related functions. One is the derivative of the other. Which one's the derivative of which? 1 over x. 1 over x is my derivative, so then my u should be ln of x. So my du is 1 over x dx. So then I write this is equal to the integral of u du, right? So I have 2y to the 1/2, or you could go ahead and write that as the square root of y. That's just kind of a personal preference thing. And then what does that give me on the right?
4
U squared over 2 plus c. And then I would immediately slash that 4 and 2, because 4 divided by 2 is 2. Right? And then I'm going to multiply through by a half, right? Because my next step's solve for y, right? Oh, you're right. I forgot we had the initial condition. I was caught up in the guiding y'all through thinking about the calculus part. This is kind of easy over here. All right, so yeah, let's go ahead and find our c. And looking at it in this view makes it harder to see as well, because I'm zoomed in on the screen and not even looking at the initial conditions. All right, so I have 2 times the square root of what? 1. That makes us happy, yes. Equals 2. Yeah, we haven't actually written ln, have we? Do you see what I'm saying? We haven't actually written the step I was going to write. So let's go ahead and write it. And we'll leave the 2's in there. 2 square root of y equals 2 ln of x squared. And I would write it with the parentheses around the ln of x and the 2. Like that, to emphasize it. Plus c. So then my arrow is going back up there now, right? So now I can say 2 times what? ln of e squared plus c. 2 times the square root of 1 is 2. What is the natural log of e? 1. Why? Because e to the what is e, right? Because isn't the natural log base e? E to the what is e? And some of y'all are playing it off like, well, I didn't need her to go through that. But I happen to know better. So that's 2 plus c. What does that make c? 0. C is 0. So that means my differential equation then is, so I'm going to ditch the c, which I can do because it's 0, right? And I'm going to go ahead and multiply both sides by a half, and I have the square root of y equals the natural log of x squared. What next? Square both sides.
Since it's squared, do you need the absolute value on the x?
Yeah, you technically do.
Okay.
But and I'm okay if y'all wait and put that in your final answer. Just don't forget or be surprised when your answer choices have absolute value bars on the x's. You're going to get very used to that very soon. So since this is our final answer, I would put the absolute value on x. And now it's to the 4th. Make sense? Okay. Oh, we got to do our domain. I was about to forget that. What is our domain? 0 to infinity. What do I need in front of the 0? Parentheses. Now let's come back to the absolute value. All right. We included the absolute value bars sort of because that's what we're supposed to do, right? Mm-hmm. But in this particular case, why could I technically not use them? That's right. If my domain restriction has already restricted me to positives, I don't technically need the absolute value. Does that make sense? Mm-hmm. That's kind of a higher level of understanding there to get that idea. Because the original, if you look at the domain of the original function, what would it have been? I mean the derivative function. It would have been 0 to infinity, right? Because we had a natural log in there, right? And so the restriction was already 0 to infinity. And you can't take the natural log of 0, which already rules out 0. But if you could take the natural log of 0, you would have ruled out 0 because of the denominator, right? So we had a couple of different things going on in there that restricted my domain down to that to start with. So what's the moral of the story of these two examples we've done as far as the domain considerations goes? Check the domain of your derivative equation before you solve it. Because a lot of times it's easier, because you'll get so caught up in the finding the integral, because that's the new stuff, that you'll forget that you knew that to start with. But if you do it from the start, then it'll make the conclusion easier. Honestly, I think that's enough to get you going. And if it's not, we'll pick up from that tomorrow.